Hello everyone, welcome to the third lecture of this module on smart building sensors. We are discussing the 11th module and we are in the 11th week of this course on microsensors and nanosensors. In the previous class, we have finished our discussion on occupancy sensors, which were very specific to the smart buildings. Okay, and we promised that we will discuss the building environmental sensors, right. The building environmental sensors were there were various building environmental sensors like temperature sensors, humidity sensors, air velocity sensors, photometric sensors, some gas sensors like for monitoring different VOCs, for monitoring emission of carbon dioxide inside a closed building. Okay. And we also talked about like particulate matter sensors like PM sensors, which is essential part of building environmental sensors, and the other sensors were like noise sensors and the smoke sensors. What we will do is we will take up these sensors one by one in little brief, and so we will see that some of the sensors we have already discussed in the previous modules and some will be new to this course. So, we will give considerable amount of time to those sensors. Okay. So, let us start our discussion with the temperature sensor. Temperature sensors plays a critical role by continuously monitoring the indoor climate conditions. Particularly, it is useful for the comfort of the person and the proper operation of the instruments which are placed inside a area. Okay. So, when these temperature sensors are utilized, it can enable the HVAC system for precise controlling and maintaining the temperature so that the occupants comfort is taken care, and at the same time it also helps in reducing the energy consumption. Okay. In module 6, we have covered temperature sensors in great detail. We have seen that there were two different kind of temperature sensors. One were based on contacts, second were the non-contact temperature sensors. The contact sensors were like RTDs, which were very popular platinum based sensors, like they were known as resistance temperature detectors. We have also seen another class of sensor which were known as thermistors, and then there were thermocouples. We have also discussed other sensors like thermopile for temperature detection, which were nothing but the series combination of thermocouples, right. And in the non-contact sensors, we were having the infrared based temperature monitors, which can of course work in both active and passive mode. Okay. However, we have not detailed like these sensors are specific for what applications, since in this module 11 and module 12 we are mostly seeing these sensors from application point of view. Particularly in this 11th module, we are seeing these sensors from the perspective of a smart building. Okay. So, we have to distinguish between a sensor which is useful for industrial application and the sensor which is useful for say smart building kind of application. Okay. So, if we compare a certain specification for industrial grade sensors for smart building, I think then it will be more clear that what kind of temperature sensors we require for our smart building. Okay. So, let us see some specifications. For example, if I talk about the span or the range of the temperature measurement. Okay. So, for industrial application, it can vary depending on what industry it is and for what application you are using it. Say it can be anything from typically from minus 50 degrees Celsius to as high as 800 degrees Celsius or sometime even higher. Okay. I mean, if you talk about blast furnace and other things, it can even go to 1800 degrees Celsius or 2000 degrees Celsius or so. Okay. However, for smart building, you do not need temperature sensor for this particular range, right. So, anything of the order of say minus 10 or minus 20 degrees Celsius, that is again for the other countries. For Indian perspective, it is even not that low. okay, and anything to around 50-55 degrees Celsius is more than enough, right. So if you talk about, if you take into consideration of the heat which is rising because of the equipments that is working inside a smart building or chimneys or other things, it can go to 150 or 200 degrees Celsius at max, okay. So if you see, if you compare these two ranges, the range for the smart building application is narrower as compared to the industrial application, okay. Similarly, for accuracy, this is little different, right. So for industrial application, accuracy of the order of plus minus 1.5 degrees Celsius to 1.8 degrees Celsius is more than enough, okay. However, it will depend on the sensor type and the application, but since we are talking in very crude sense, I think I am able to communicate with this plus minus 1.5 and plus minus 1.8 degrees Celsius. However, if you see the relative requirement for a smart building, it is anything around plus minus 0.1 degrees Celsius to around plus minus 0.5 degrees Celsius. Again, it will depend on what kind of sensor you are utilizing and for what intended application, okay. But if you compare these two accuracy ranges, the requirement for the smart building application is like it require higher accuracy as compared to the industrial application, okay. Similarly, for response time, anything between 8 to 15 seconds is more than enough for a industrial application. However, for smart buildings, you need quicker response, like anything from 1 to 5 seconds is good enough, okay. Similarly, if you see the output signal for industrial sensors, mostly you will see that they use analog kind of instruments, analog kind of temperature sensors, while the smart building temperature sensors are mostly digital. Of course, it also require analog sensors, but mostly it rely upon digital temperature sensors, okay. The robustness requirement for industry is very high, okay. However, you do not need a very robust kind of temperature, very rugged kind of temperature sensor for smart building application, because your sensor is not going to see very harsh ambient. It is lying inside a clean built area. So that kind of ruggedness is not required, okay. For the industrial application, it has to see several vibrations, dust, water, different chemicals, okay. However, it sees a decent kind of ambient inside a built area, okay. Of course, it has to be dust resist or moisture resist, but then the harsh ambient that we just talked about in industrial condition is not required in this case, okay. So you can say that the robustness required for smart building is kind of moderate, okay. Similarly, if you compare the power requirement, the industrial application devices can be loop powered or it can be directly connected to mains. But however, mostly the smart building devices, smart building temperature sensors are low power devices, because they have to be mostly wirelessly connected, okay, and in certain cases it can be battery operated also, okay. Therefore, I can say that the temperature sensor requirement for smart building is like particularly in term of power is like it should be a low power device, okay. And then for the deployment, it should be unobstructive, and the integration is essential, okay. So when I say integration, it means the integration with the other existing tools like HVAC systems or any other systems with which it will work in conjugation. For example, with a humidity sensor, for example. So we know that humidity sensor with a temperature sensors can generate a data which we known as humidex, right. So humidity at particular temperature can give you a data which is known as humidex, and the comfort level of the occupant will depend on the humidex, not exactly on the temperature, neither based on temperature nor based on the humidity. So it is the humidex actually which define the comfort level of the person, okay. So mostly this temperature sensor has to work in conjugation with other devices like humidity or gas sensors. That's why its deployment is very important in case of smart building. However, for industrial application, of course, you require a heavy duty operation, and the device should be field serviceable, but then the deployment is more kind of fixed. So, you do not need unobstructive or that kind of requirement is not possessed over here. Okay. So, if I talk about digital temperature sensor, which we just talked some time back, actually these devices are pre-calibrated and they have a digital interface. I mean, it can use a number of protocols like I2C, SPI or one wire. I mean, there are number of protocols with which it can communicate. Okay. However, the advantage of these devices are they are compact and mostly very energy efficient. Okay. So, it can help in real time HVAC optimization. It will ensure the thermal comfort by measuring the real time temperature. Okay. The energy savings are of course being enabled by these sensors by measuring the temperature with more accuracy. Okay. Advantage of these sensors, particularly in the current scenario, is they are mostly IoT enabled. Okay. So, IoT connectivity helps us in taking the data over the internet. So, you do not need to actually monitor these temperature sensor manually. Okay. Then these digital sensors nowadays, all the devices are compatible with this digital temperature sensor. So, they have a great compatibility with the integration with the say building management systems. Okay. The operation of these devices are pretty simple. We have already talked about IC based temperature sensor. Okay. So, these sensors are basically based on different ICs which uses certain band gap or certain diode or even based on certain transistors. Okay, to measure the temperature. We have seen that in detail in module 6. Okay. The next thing in this device are the digital logics which is inside the chip which processes the signals. Okay, and output is sent via the different protocol that we have just talked about to the controller, and then data is logged, monitored and used for the automated control. Okay. Similarly, with the temperature sensor, we have humidity sensors. Humidity sensors, we know that it is used for monitoring the humidity, but the role of humidity inside a smart building is enormous. Okay. So, the humidity sensors helps in climate control by balancing the comfort and the health of the occupant by maintaining the optimal humidity conditions inside a living area. It also helps in energy optimization by automating the humidification and dehumidification inside the built area by reducing unnecessary HVAC uses and lowering the energy consumption. Okay. It also helps in air quality management by supporting allergy management, and it also enhances the occupants well-being by doing this. Okay. Then it also supports predictive maintenance, particularly the early leak or malfunction detection through abnormal humidity readings in certain systems where there is a chance of increase in humidity by certain leakage, particularly those systems which require water for its operation, particularly like chillers and other things. Okay. So, we have talked about humidity sensor in module 5. So, essentially those sensors are applicable over here. We have seen that a number of transduction techniques can be utilized for detection of humidity like optical, gravimetric, piezoresistive, magnetoelastic, capacitive and resistive. All these techniques, the sensors based on all these techniques are more or less applicable in the smart building. However, we have seen in the case of temperature sensor that what is the requirement in case of smart building. We have seen that in the context of temperature sensor, but then that can be extended for the humidity sensing also. All right. Then the advantage of digital humidity sensors are like they have direct digital outputs, right. So, you do not need basically another layer of analog to digital conversion. Okay. So, they can be easily integrated with the microcontrollers and the IoT platforms, okay, like ESP32 or any other. Okay. They often combined with the temperature sensor as well as with the pressure detectors, right. Mostly they are pre-calibrated, okay, and they require a very less amount of power for their operations, right. So, these are certain advantages of the digital humidity sensors, but the module 5 is very important, where we talked about humidity sensor. Most of the sensor that we have discussed there is applicable in this section. Okay. Another set of sensors which are very crucial for measurement of or monitoring the building environment is the air velocity sensor, and till module 10 we have not discussed any air velocity sensor. So, what we will do is we will give considerable amount of time to understand air velocity sensor and why it is required even in a smart building. Okay. So, air velocity sensors are used to measure the airflow rate, its velocity, speed and direction in the built environment. Okay. They play a crucial role in enhancing building automation, HVAC control and energy efficiency in a smart building. Okay. They provide real time data for optimizing airflow, ensuring occupant comfort and maintaining healthy indoor environment. Basically, in any smart building you have a certain level of airflow. It can be a laminar flow or it can be turbulence flow, depending on what kind of building architecture it is, or what kind of architecture it has adopted. Okay. Depending on that, the air circulations are designed in a smart building. Okay. So, this air velocity sensor will measure that flow of air as well as its direction and the rate, okay, by which it can help us in improving the air circulation in a smart building. Okay. So, let us see how air velocity sensors are utilized. They measure the speed of airflow in HVAC ducts, clean rooms and in the controlled environment. Okay. They used to monitor, control and regulate ventilation, ensuring adequate airflow for air quality as well as for system efficiency. Okay. They often integrated with a building management system or BMS via analog or via the digital outputs, depending on what kind of device it is. Okay. Typically, this air velocity sensors are of 4 different types. One is thermal anemometer. Please note that this air velocity sensor, there is another name for this air velocity sensor which is known as anemometer. Okay. So, there are 4 different kind of air velocity sensor. The first is thermal anemometer, second is vane anemometer, third is ultrasonic sensor based anemometers, and then you have differential pressure sensors based anemometers. Okay. So, we will see what they are and what is the principle of operation of these sensors. Out of these 4, thermal anemometers are very popular, and that is why this thermal anemometers has been fabricated using the MEMS technology as well. So, what we will do is, after we discuss this 4 different air velocity sensor, we will also talk about MEMS sensor, and we will see that how this micro electromechanical systems can be extended for the measurement of air velocity. All right. So, let us talk about thermal anemometers first. These thermal anemometer are also known as hot wire anemometer because of the use of utilization of a wire or the hotness or coldness of that particular wire. Okay. So, let us see what is a hot wire anemometer or a thermal anemometer. Okay. The hot wire anemometer operates on the principle of heat transfer from a heated thin wire to surrounding air which is flowing over the wire. Okay. So, the key element of this principle are a very fine wire. This is the wire I am talking about. This is the schematic of the hot wire anemometer. of a very fine wire usually made up of metals like tungsten or platinum is electrically heated by passing a current through it. Okay. So, when I say electrically heated, I mean to say the I square R heating, right. So, a very fine wire of this tungsten or platinum is electrically heated by passing a current through it. Okay. Now, when you pass the current, the temperature will rise above the ambient air temperature. Okay. Now, since you are utilizing it to measure the air flow, okay, this will be placed in such a way that the air is flowing across it. Okay. So, when this air flows past the hot wire, it cools the wire by convective heat transfer. Okay. So, this air, of course, it is at cooler temperature as compared to the wire, because I have heated it through this through passing of the current. Okay. By convection, this air will carry heat. Okay. Now, since this heat is certain amount of heat from this wire is getting carried away by this air, okay, what will happen is this wire will see a drop in the temperature. Okay. Now, the rate at which the wire loses heat depends on the air velocity, right. So, higher the velocity, it increases the cooling rate, right. This cooling causes the wire's temperature to drop, which changes the electrical resistance, because resistance depend on the temperature. We have already seen that in different modules. Okay. Now, by measuring the resistance change or the current required to maintain a constant temperature, allow the person to determine the flow of the air or the rate of flow of the air or the velocity of the air which is flowing on the wire. Okay. The principle is pretty simple. Okay. There are two different modes in which this anemometer can operate, a hot wire anemometer can operate. One is constant current method and another is constant temperature method. Okay. Let us see what is constant current method. Okay. A constant current is passed through the wire, as the name suggests, constant current method. Okay. So, you have this wire, okay, you have this air flowing on it, okay, and when this air carries certain amount of heat because of convection, of course, it will see certain dip in the temperature, and because of which the resistance will change. Okay. Right. So, you have to maintain the temperature at which initially this wire was. Okay. So, it will require certain increase or decrease in the current levels. Okay. So, there is multiple ways that can be done. Okay. However, what we are seeing in this method is the constant current method. As the name suggests, a constant current is passed through the wire. Okay. As air velocity increases, more heat is removed and wire temperature will get down. Okay. This causes the wire resistance to decrease and the voltage across the wire changes and is correlated to the flow velocity or the air flow velocity. Okay. The method is pretty simple. Okay. However, there are certain issues with the constant current method, like the wire can burn itself if the cooling flow is too low, or if the flow is very high, the wire will not even be, it will not heat up till the level from which the data can be extracted. Okay. So, both the cases there are certain issues. So, people has come up with another method which is known as constant temperature method, which I was just talking about some time back. Like I was talking, like if this is a thin wire and if heat is getting extracted from it, the temperature will go down, and then you have to change the current passing through it, okay, to maintain the temperature. Okay. This is the constant temperature method. Okay. The wire is held at a constant temperature now, not at constant current. Okay. The wire is held at a constant temperature by adjusting the heating current. Okay. Increased air velocity increases cooling, so more current is needed to maintain the wire's temperature. Now, the current required to keep the wire temperature constant is actually directly proportional to the air velocity. Okay. Now, this method provides a faster response and better accuracy, and it is more commonly used. So, you will see that most of the devices utilizes this constant temperature mode. Okay. For all conditions, energy balance equation has to be used to describe this heating and cooling of the wire. Okay. Based on this heating equation only these sensors are based. Okay. This equation can further be solved to determine the velocity of the air flowing on the wire. Okay. So, at steady state the electrical heat input equals the heat lost in the air. Okay. So, I square R was the electrical heating that were provided to the wire of resistance R. Okay. So, I square R is the heat supply and this is equal to this equation A V into rho plus B and this is to power n. Okay, where I and R I have just talked, like I was the current flowing through this wire and R is the resistance, V is the velocity of the air. Okay, rho is the density of the air. Okay, A, B and n, these three are empirical constants based on sensor and the air properties. Okay. So, this is the most important type of anemometer, but then there are other kind of anemometers also like vane anemometer. Okay. So, vane anemometer feature a small free spinning turbine, something like this. Okay. It rotates as air flows through or flows over it. Okay. The rotational speed of the vane is directly proportional to the airflow velocity. Okay. And this speed is measured and converted into an airflow reading. Okay. So, this is a simple device. By measuring this rotating vane's speed, you can calculate this is a kind of straightforward method, but then it require, it has lot of moving parts. So, it will have lot of wear and tears. Okay. So, you have other kind of anemometers also like ultrasonic anemometer. Okay. The ultrasonic anemometers are advanced sensors using ultrasonic sound waves to measure wind speed and direction with very high precision. Okay. Unlike the mechanical anemometers like vane anemometer, they have actually no moving part at all. Okay. Therefore, the ultrasonic anemometer are maintenance free, they are reliable and have rapid response operation. Okay. Usually their arrangements are in pairs. So, ultrasonic transducers are arranged usually to 4 pairs in a geometric pattern. Okay. The other pairs of course are not shown over here, then there are other transducers also placed over here. Okay. These transducers can send and receive ultrasonic waves, very similar to the ultrasonic sensors that we have seen previously. The same sensor can, same transducer can send the data, send the ultrasonic sound, and the same can act as a receiver. Okay. The advantage of this ultrasonic anemometers are the first and foremost is you do not have any moving part, very similar to the vane anemometer where there were several moving parts. Okay. So, when there is no moving part means it ensure the durability and maintenance is also less. Okay. They are suitable for turbulent wind measurement for which the vane anemometers are of course not suitable. Okay. They can measure 2D or 3D wind components also. Okay. They work efficiently in very harsh ambient that we have just seen. Okay. Even it can be used in rainy season or in snow or even in a sand or in very harsh dust and that kind of environment, because it has nothing to do with those conditions. It works on the reflection of the sound wave. Okay. Since sound waves are involved, their response time is quick and they can be utilized for real time wind monitoring. Okay. Then another kind of anemometers are differential pressure sensor based anemometer or differential pressure based anemometers. These anemometers use a restriction placed in a airflow. Okay. The restriction I mean to say that like a pitot tube or a orifice plate or a venturi, I mean depending on what accuracy you require and what kind of restriction is available with you. Okay. Now, the device a simple structure of the device is shown over here. This represents some electronic circuit which is required for proper operation of this device. Okay. The device measure the difference in the pressure between 2 points before and after the restriction. Okay. And according to the Bernoulli's equation, the greater the wind speed, the higher the pressure difference is. Okay. The differential pressure sensor converts this difference into an electrically measurable signal or some electrical signal, like in the form of current or in the form of voltage. Okay. Now, this air velocity is calculated using this particular equation, where this V is the wind speed and C is the calibration coefficient. This is very popular equation used in fluid dynamics. This V is equal to C root 2 delta P by rho, where delta P is the measured pressure difference and this rho is the air density. Okay. By using this equation, this differential pressure sensors can tell you about the wind speed. Okay. The advantage of differential pressure sensors are enormous, like it do not have any moving part, very similar to the ultrasonic sensor. So, its durability is increased and of course, it require low maintenance. Okay. Then it has versatile installation, so it can measure low and high air velocities all. Okay. Their linearity is good because flow is proportional to the square root of the pressure difference. Okay. And these devices are compact and reliable. Okay. However, they have certain limitations also, like sensitivity decreases at very low wind speed. They require density compensation for variable temperature and pressure conditions. Okay. And then accumulation of dirt can form certain debris inside the orifices or tubes, which can of course affect the accuracy of the device. So, then you have to mechanically clean it. Okay. Then another kind of, this is of course not a kind of anemometer, but the technology that can be used for modern anemometers to be developed, which is MEMS based anemometers. Okay. So, the micro electromechanical system based anemometers are advanced wind speed and direction monitors, which are fabricated using micro scale semiconductor manufacturing techniques, right. So, these devices offer high sensitivity, low power consumption. It can be miniaturized because it can be fabricated with a dimension of even less than a millimeter. Okay. And of course, since it is made on silicon platform, their integrated capabilities are very high. Okay. So, therefore, these MEMS based anemometers are ideal for utilization in smart buildings. Okay. These MEMS based anemometers are again are of two type. One is the thermal anemometer, very similar to what we have seen for the hot wire anemometer, and another is the solid state anemometers. Okay. The thermal anemometer are very similar to what we have seen. It utilizes however a micro fabricated heater and adjacent temperature sensors on a single silicon chip. Now, the heater is heated by electrical current, as we have seen in case of the hot wire based thermometers. Okay. The incoming airflow cools the heater and the temperature drops, or the power changes to maintain the constant temperature, and this is measured. Okay. The rate of cooling is proportional to of course the wind speed. Okay. So, there are various variants of these thermal anemometers, like constant temperature anemometers, constant power anemometers, and the calorimetric devices, which work on the differential temperature measurement in the upstream and the downstream. Okay. Then another kind of MEMS based anemometers are the solid state anemometers, which include the flexible beams or the diaphragms which bend under the airflow. You know that on a silicon wafer it is not very difficult to etch out and make cantilevers. Okay. So, those kind of cantilevers are utilized in the solid state anemometers, and these cantilevers or diaphragm can actually flex when there is a change in the airflow. Okay. And the displacement is measured using a piezoresistive or capacitive sensors, and this can be translated into the wind speed. Okay. So, there are various advantages of using MEMS platform for the development of anemometers, like they enables integration with other sensors very easily on a single chip. These other sensors we have seen can be temperature sensors or humidity sensors. Okay. They are suited for battery operated wireless or remote monitoring system because of their miniaturized size. Okay. They are capable of detecting very low wind speed okay, even down to 0 to 1 meter per second or even smaller than that, because of the very small cantilever associated with it, and the deflection of this cantilever or the deflection of the diaphragm can easily be certain voltage change or certain current change, which can be easily measured. Okay. Then they are highly reliable, durable, and maintenance free operation is possible. Okay. Then these MEMS based tiny chips are ideal for turbulent or rapidly changing airflow measurement. Okay. And this MEMS solid state construction resists the vibration and shock, and then I can make a weatherproofed MEMS solid state anemometer. Okay. However, not all advantages are only associated with the MEMS anemometers. There are certain limitations also, like performance can drop in heavily contaminated or saturated environments due to deposition of these contaminants from the ambient on the chip. Okay. Some MEMS thermal anemometers may require careful calibration, particularly for the temperature and pressure compensations. Okay. So, these are different anemometers, and the fabrication of each we cannot discuss, of course, but then certain kind of anemometer we can definitely discuss, like we have just talked about the MEMS based anemometers. Okay. So, if I go to the list of building environmental sensors, I can say that I have now talked about temperature, humidity, and air velocity sensors. However, the discussion on photometric sensors, gas sensors, very limited to the built environments. Okay. Then particulate matter sensors, smoke sensors, and noise sensors has to be taken up. Okay. So, we have to discuss all these sensors which has not been discussed till yet. Okay. So, we will meet again in the next class, and we will start our discussion on photometric sensors. Thank you.